Okay, I would like to say something about the laws of total expectation and variance. Now, these are in the textbook notes, the 325 book Stochastic Processes PDF. I want to give a separate explanation. So here is a map that represents a probabilistic situation. So there's several rectangular regions. You can see the square, the gray borders. Here's one here. Here's one here. And each rectangular region is labeled by a different word. You may not be able to read it, but this one says healthcare, financial, energy, utilities, and so on. Now, each sub-region within that region represents a different commodity. And the brightness of the color indicates the percent change in stock market share price for that commodity. So we have kind of a map of the stock market where we have different commodities. Some prices go up because they're represented by bright rectangles, and some prices go down because they're represented by dark rectangles. This is something that's called a tree map, which is often used in business intelligence to represent data. So we have these different rectangles. They're different brightnesses. They're also different sizes. The size of the region determines the market worth for that commodity. So for instance, a large rectangle represents a large share of the market. Small rectangle represents a small share of the market. So this black rectangle represents a commodity that takes a fairly small share of the energy market that reduced in percent change in percent market share, percent market share price. So the question is, what about the mean percentage change in the entire market? We can phrase that question as, what is the mean brightness, which represents the mean percentage change in stock market price for the entire map? Of course, we're really interested in the number, but visually we can understand what's going on if we think about brightness. So let's think about the question, how would we obtain the average brightness over this entire map? Now, you could also phrase this question as follows. Imagine choosing a random point from this entire map. What would the expected brightness be? Now, of course, to get close to the expected brightness, you'd have to choose many, many, many random points. But those random points eventually would represent the brightness of the entire region. They would cover the entire region, and that would be the same thing as averaging the brightness over the region. Right? So let's represent the brightness by a random variable, x, and the market sector by y. So we have, for instance, capital goods, that's one value of y. We could say that's y equals 1. Transport, that's y equals 2. Consumer staples, that's y equals 3, and so on. The value of y doesn't really matter because what we're concerned about is the value of x. Now, the value of x will depend on the value of y, but the value of y is not going to be an arithmetic contribution to the expected brightness. Now, we could find the average brightness as follows. We could find the average for each market sector, then average the averages. So, for instance, you could look up here and what's the average brightness for energy? Now, that would actually be pretty bright if we averaged over only the commodities in energy. So that would give a fairly bright contribution for this sector. What's the average brightness for this one? Basic materials. Looks like it's a little bit darker. So we'd have a darker average here. Now, if you imagine taking the average for each one of these market sectors, you'd get one color for each sector. So this entire healthcare square would become one color that represents the average of all the colors within that square. And this one too, financial. You get one color for this entire square. So you'd get if you did the averages, you'd get a map with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, about 11 or 12 colors, and each color would represent an average. Then to get the total average of the overall map, you take the average of those averages. So the idea is you're taking an average of averages. And that's the entire idea behind the law of total expectation. The expectation of x given y means I look at each sector in turn and get an average value for that sector. Then I take the expectation over y. After I get my average squares, then I average those together and get the total average. So that's how this law of total expectation works. Now let's consider the law of total variance. We've got the very same situation here, the very same map, and we want the variation in brightness for the entire map. All right, so we could phrase this question similarly to the way we did the other one. So if we choose a sample of random points in the map, what's the expected variance in brightness in the sample? Now you know how to define variance of a sample. It's the expected value of the brightness squared minus the square of the expected value of the brightness. So you can see there's quite a bit of variance in brightness. So how would you compute this based on the data that we have in this map? Well, instead of, so let's use the same x and y, and we're wanting the variance of x over the entire market. Now, within each sector, there's going to be a variance, right? There's a lot of variance in this basic material. Some is very dark, some is very bright. In energy, there's much less variance. It's mostly bright. So you can see the variance really depends on the market. Transport, there's not much variance. So if we could imagine giving one variance for each one of these squares, you get a different color that represents each square. So you're going to have a variance within each sector, and that's going to contribute to the total variance. Now there's an additional variance, because once you color each square by one color, you still have a variation between squares. Now it turns out that the variation between squares and the variation within squares simply add. This is related to the fact that if you have independent random variables, their variances add. So that gives you the law of total variance. So here you have, so let me just identify what these are. This here, variance of expectation, let's see if I got this. This here is the variance over y of the expectation of x given y. So this is going to be the average value of x over each square. So this is the average of x over each square. And we're looking at the variance over y. So this part here is the variance between squares. That's the variance between squares. And by square, I mean value of y. Now this one here is the variance within each square. So that's the variance within. Okay. And then this you're taking the average over the value of y for the variance within each square. So two pieces of the variance, those two pieces add, and we get an overall variance as a result. Now, I've got two problems here that illustrate this that I want you to do in class. I'll just show these. Here we have a value. We have two random variables. One will correspond to x, and one will correspond to y. So you can figure out which one is x and which one is y. And here's another one where we have an x and a y. All right. Now, there's a special case of this situation, which is called randomly stopped sum. So, as I said, this is a special case of these laws of expectation and variance. So, in this case, you have a number of terms in the sum which varies randomly. And each term in the sum is independent, identically distributed. So you could think, for instance, of flipping a coin, and you don't always flip the coin the same number of times. You flip a certain number of times depending on the outcome. So y would be the number of times you flip the coin, and then each outcome would be what I'm writing here as xj. So the total sum we refer to as x. It's the sum of y independent, identically distributed random variables, but y itself is a random variable. So I'm going to use when I talk about the distribution of one of these independent identically distributed random variables, I'm just going to use x1 to represent the distribution, because each one of these different x's has the same distribution. You could think of each one of these as representing one flip of a coin. So the first flip and the second flip have the same distribution. There's no difference in the probabilities that are computed based on those different flips. Right, now let's see what the law of total expectation says about this situation. So if we go over here, this is the law of total expectation. We still have two random variables. We have big X, which is the sum of independent identically distributed random variables, and big Y, which is the number of copies of those random variables. Now, what is the expectation of X given Y? Well, X is a sum of Y independent identically distributed random variables. When you take the expectation of a sum of random variables, that's the sum of the expectation. Now, in this case, when we take expectation of X given Y, Y is treated as a constant value. X given Y means you take Y as constant and compute X. So then X would be the sum of Y identically distributed independent copies. So the expectation of this sum of Y copies is simply equal to Y times the expected value of one copy. So I can write this expectation for X given Y, meaning you have Y copies of this random variable with distribution X1, as Y times the expected value of one copy. Okay, so that's for a particular value of Y. Now at this point, we want to use a assumption of independence and say that Y and Xi are independent. And we'll get that the expectation of Y times expected X1 can just be separated out. That in fact X1 or all of the X's don't depend on the value of Y. So we're using this assumption, which is important to guarantee this. So you need to make sure when you're applying this rule that the rule for stopping the sum doesn't depend on the values within the sum. Right? So let's go on and do the same thing with variance. Okay, so let's do the variance of the randomly stopped sum. So we have the same law of total variance, and let's decompose that in this case. Now, in this case, remember that X is the sum of identically distributed random variables, and here we're taking Y as a constant. So this X given Y is the sum of Y copies of X1. So we can write this expectation as Y times the expected value of X1. And when we take the variance over Y of that, well, we'll see what that is in the next step. So let's look at this one here. From the law of total variance, we get the first term that contributes to the variance of X as the expectation over Y of the variance of X given Y. Now here again, X given Y is a sum of Y copies of X1. Now these copies are independent, so if I have a sum of Y copies of X1 that are independent, then that simply gives me Y times the variance of one copy. When I take the expectation of Y, expectation with respect to Y over this, again using the assumption that X and Y are independent, we get that each copy of X and Y are independent. We can pull out this expectation of Y, and we get expectation of Y times the variance of X1 plus the variance of Y times the expectation of X1. So this gives us a case of randomly stopped sum. Now, often in the book, I think he uses N instead of Y, but I used Y to try to relate this randomly stopped sum to the law of total expectation. So down here, I've screen clipped the result from the lecture notes, so you can see the way that he writes it. So just to summarize, suppose x1 through x2, etc. have the same mean mu and variance sigma squared. So mu is what I'm calling expectation of x1. He's calling that mu, so let me just denote that. This is what we're calling mu here. Okay. And variance sigma squared, so this is what he's calling sigma squared here. And x1 through x2 and so on, and are mutually independent. Remember, I used that here to get the expectation. So let Tn be the sum of the randomly stopped sum. This Tn is what I'm calling x. Okay. So by the result that he has is expectation of Tn is equal to mu times expectation of n. So his Tn was what I'm calling x. His mu is what I'm calling the expectation of x1, and his n is what I'm calling y. The same thing here. When he does the variance, this Tn is what I'm calling x. This sigma squared is what I'm calling variance of x1. This expectation of n is what I'm calling expectation of y. And then we have mu squared times the variance of n. All right, so it's good we made this comparison because he is correct and what I have up here is not correct. Let me go back and fix this. When you take the variance of a constant times a random variable, you need to take the square of the constant. So that is a square there. So that my equation here matches up with his, and everything should be okay. Now I have one example of a randomly stopped sum here that you can do, and we'll spend some time in class doing this. All right.